Well, hello, folks. Today we're going to talk a little bit about the electromagnetic spectrum. And just as a disclaimer, I didn't put all this together. A couple of my female assistants did, so it's kind of girly looking. Sorry about that. Anyway, so we should start off with what is a wave. Light comes as both photons and particles and waves. And you've all seen this before, but it's important to point out that what we're going to focus on today is not wave height or even amplitude. We're going to focus on wavelength, the distance from the top of a crest to the top of the next crest. Because a change in that wavelength determines not only the frequency of the electromagnetic energy or the light energy, but it also determines what type of light we're looking at. So let's explore it. So, for instance, these waves are all traveling about the same speed, okay? But these waves have a much shorter wavelength than down here, okay? So they have a much higher frequency. Frequency is just the number of waves that pass a given time every second. So here, obviously, once a second, you're going to get 3 waves. If all 3 of these waves pass in a given second, you're going to get that's a frequency of 3 waves per second. Up here, if it's the same time span from here to there, you're obviously getting many more than 3. So these waves are a higher pitch. These waves would be a lower pitch. That's why they show you the smaller instrument versus the larger instrument. That's what they're trying to get across here. Now that's of course describing sound, but the same applies for light waves. So moving on, we can also convert. I would write down all this stuff. Just pause it here and write all this down. It's cool to be able to convert from wavelength to frequency. And just a little practice for you. This c is the speed of light. So take the speed of light divided by the wavelength in meters, and you get frequency, and so forth. Question for class. What is the wavelength of a radio station that transmits at a frequency of 102.0 megahertz in the FM band? So just something to think about. And come in with an answer to class next time. Alright, so here's the electromagnetic spectrum. You may not remember it, but you've been introduced to this before. The part we're concerned about, the whole thing, honestly, but our eyes are only concerned with visible. So all of these, this entire spectrum is light. Light emits in a wide range of frequencies. This is the frequency band. All the way, as we call frequency band width of light is all the way from radio all the way up to gamma. Our eyes are only sensitive. Our eyes can only detect visible radiation. We're going to spend a lot of time looking at the radio end of things because radio has a lot more versatility. But you're familiar with visible, and that's where you get the Roy G. Biv colors. So let's start at the far end. We'll start at the left with radio waves. These vary greatly in size and can be very, very long. All right, so that's typical radio wave stuff. Even the size of football stadiums. That's how big the wavelength of a radio wave can be. Even bigger than that, and much smaller than that, down in the order of centimeters. It's a very wide part of the entire frequency band of visible light. The next shortest is microwaves, and already we're getting to the point where our frequencies are pretty high, and we're not quite at visible yet, but the wavelengths are getting pretty tiny. These are used for long range transmissions. In fact, some of the dish network transmissions that you get your televisions on are transmitted via microwave radiation. So that's still light, it's just microwave. It's also used to cook food. Sorry about that Hello Kitty microwave there. Alright, so there's something the size of a microwave. A ladybug, only about a couple millimeters in wavelength. Alright, infrared. We sense it as heat. Our eyes aren't sensitive to it. Bees are, which is why if you go around a hive and you get really uptight, your blood pressure rises, and your body temperature rises a little bit, they sense it and then they want to sting you. But the energy in infrared is not high enough to cause burns. That's ultraviolet, which is on the other end of visible. Which brings us to, infrared also is about the size of a pinhead, like most of you. Anyway, moving on. Visible light is what you're all familiar with. It's what you're using to view this presentation. Yes, you're using visible light. Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. Okay, we see these colors due to the reflection and absorption of various wavelengths of light off of objects or through the atmosphere. Okay, that's what our eyes are sensitive to. And of course, bacteria are about, these are not obviously the same size as bacteria, but actual bacteria are about the size of visible light waves. Alright, ultraviolet used by bees. I'm sorry, this is used by bees, not infrared. My bad. And long-term exposure, as you all know, the old ozone layer discussion and whatnot. Without ozone layer, we'd have too much UV radiation, and you end up with sunburn or cancer in the end. They're also about the size of a water molecule. So now we're on the order of the size of atoms with ultraviolet radiation. Okay, X-ray light, which is used in medicine. This is very energetic waves. They're very short wavelengths, very high frequencies. They don't make it. X-rays from space don't make it into the Earth's atmosphere. So if you're going to use a telescope to view an X-rays, it has to be in orbit. They can be very dangerous at high exposures. So you got to watch out. This is why you go to the dentist and they put a big lead apron over you, for instance. That's one of the reasons they do that. And they're about the size of your typical atom as well. So I'm sorry. The previous ones, ultraviolet, were the size of a molecule of water. These are the size of an atom within a molecule. My bad. Trying to go through this too quickly, obviously. All right, gamma rays. These are mostly from radiation from radioactive materials. They're also tend to be absorbed by the Earth's atmosphere and can be very dangerous because these are the highest and most energetic forms of light that exist. And they're about the size. The wavelength is about the size of an atomic nucleus. Something bigger than hydrogen, okay? Because hydrogen only has a proton in the nucleus, all right? So it's got to be something like in the order of carbon or something like that at least. All right. Now this is kind of cool. This is a variety of different pictures of the Milky Way in various wavelengths of light. So invisible light, optical is the other word we use for visible rather. This is what you would see either through a telescope or in a very dark area, like say back in craters, if you were looking at the Milky Way. All right, where there's not much in the way of light pollution. But the Milky Way can be viewed in all these other wavelengths because light, like I said, has a very wide frequency band. It's not just visible. Visible is very narrow. But as you can see, the frequency gets much shorter, or well, much more frequent, and the wavelengths get shorter down here, and they get longer up here. Okay, so there's what the galaxy looks like in gamma. There's what it looks like in X-ray, optical, and then near infrared. You can really start to see the central bulge of the galaxy right there. The nuclear center is Sagittarius A. That's what it looks like in infrared. That's the heat coming out of the galactic plane. This is the plane of the galaxy, by the way, if you haven't figured that out. This is infrared. Now these are all radio spectra. Okay, and most people who study the galaxy use radio waves to do so. And so this is molecular hydrogen. This is at about 20 centimeters wavelength. You'll be using 20 centimeter wavelengths, and when you go to the observatory in November, you'll be looking at the galaxy using actually 21 centimeters. It's the wavelength of at which hydrogen emits. Okay, and then of course the radio continuum here. This is at 2.5 gigahertz. This is another way of looking at atomic hydrogen, and then of course another. So there's a lot of radio is really great for astronomy, which is why we spend so much time on it this year. Okay, so they tried giving me credit for designing this, but Megan Weaver and Adria Sirico, thank you. The rest of you, good luck, and we'll talk about this more in class.